So for our next section of concept derivation numericals, we are going to work with something called as ideal fluid. Okay, guys. So the thing is, an ideal fluid is basically a simplified version of real world fluid that we get to see. It's actually a step away from the complexity that the real world fluids have. So this model, this ideal fluid, it ignores like viscosity, turbulence, and compressibility. So because of these assumptions per se, it makes it easier for us to study and understand the basic behavior of fluids. So by assuming few ideal conditions, we actually can focus on the core principle, and we are able to carry out certain derivation that helps us explain how fluid moves and interacts with different situations. Okay, so that's why we are looking into ideal fluid. But actually, honestly, even though ideal fluid, they don't really exist, the concept is very much useful for many real world actually flow. Like air moving at a higher speed, right? There we can look at them as being ideal fluid. They behave like ideal fluid. Water flowing in a larger pipes or rivers, and even atmospheric and ocean currents, right? I'm sure you guys know about ocean currents. Even atmospheric currents are also there. So we can approximate whatever you are studying over here, we can approximate and use it over there as well. So before we dive into application numericals of course, of using ideal fluid or of ideal fluid, we'll first understand what makes an ideal fluid. Very first thing is we are looking at steady flow. So fluid moves the same way at every point. What does it mean? Okay, this actually we have gone through at certain point of time. So let me put it this way. Okay, so basically, say you have a flow case and you are observing one single point. You're just watching that. You see that there's one molecule that comes in. It has a particular velocity. Okay. Next molecules comes in ideal fluid. Okay, we are considering ideal fluid that is flowing through this pipe. So this is a pipe, and we are watching one particular point. This particle too will have the same velocity. That is, the speed and direction will be same. You see the next particle, you observe that this too will have the same speed and direction. You will observe the next particle, and this keeps happening. So as and when you keep observing, we get to see that they have the same velocity and direction. So that's an ideal fluid. So basically, an ideal fluid, you get to see the same wherever you see a particular behavior. Say I saw a particular behavior by a particular set of molecules. The same behavior will be shown by all the molecules provided the condition remains the same. Okay, so for a given condition, whomsoever you take, whichever molecule you take from the ideal fluid, they'll behave the same way. And so the first point, you see a steady flow. So it looks stationary basically. It looks, again, you can web search laminar flow. So that particular, whatever you see is a case of steady flow. It's not sticky, there's no viscosity, the density is constant, there's no spinning or swirling motion, right? It won't go here and there and all of that. No internal drag because there's no viscosity, so we don't see internal drag. So these are the basic conditions that we start off with. And built on this is quite a few concepts that we're going to see. But yeah, this you guys need to know. How you define rigid object, right? We have a definite idea of rigid object. Rigid object is an hypothetical situation. Ideal fluid also is an hypothetical situation. So we first look at hypothetical ideal situation, understand that, and then we move on to the real world. That's how knowledge is built. So, and that's why we should learn about the characteristics of ideal fluid, build our initial concept. It makes it easier for us to understand few things. And from there, we move on to the next portion. Okay. So you have to pause. You need to know all of this. So there's no other option.